Okay, here we go again. All right. This is your friendly heavy physics teacher. Once again, college physics lesson. This is unit 9, lesson 6 and 7. A very abbreviated version of AC versus DC power generation. And then we're going to get all pretty heavy into transformers for this. Transformers as in the electrical devices, not robots in disguise. No appearances by Optimus Prime or Megatron. Okay? All right, first things first. I really got to define this for you. Lenz's Law. Lenz's Law can be thought of almost as a form of Newton's third law for electromagnetism. All right? Specifically electromagnetic induction. All right? Now, at its essence, now make sure you check on the supplemental notes this definition again. Lenz's law. An induced current in a conductor will produce its own magnetic field opposing the external magnetic field that induced the current in the first place. Holy cow. What in the world does that mean? Okay, so if you'll recall, I showed you this at our last online session. All right. Here's what Lenz's law means for this. We can figure out which way the current is going to flow in this loop of wire here based upon how we know this is moving and the magnetic field that's interacting with it. Remember, this area, the rectangular area of the loop of wire here, is going to change as you move the wire out. Excuse my dog in the background. My wife just got back from shopping, okay? And I'm not going to edit it out because I don't know how to do the editing stuff yet, all right? So if we pull this loop of wire out over that way, okay, moving it to the right, based on the diagram here, okay, that means that the area is going to decrease with respect to the magnetic field, what's exposed to the magnetic field, and that's going to induce an EMF in the wire. Well, that means that there's going to be a polarity on the ends here. Well, if you induce a voltage and then you connect that to something that can use that voltage, you're going to induce a current. So which way will the current flow in this? That's what Lenz's law is for. Okay? So, the motion induces an EMF in the loop. If the loop is connected to a load, then use the second right-hand rule to determine the direction of the current. So, that current will produce its own magnetic field. It will produce its own magnetic field that will oppose the magnetic field that made the current in the first place. That doesn't mean it'll be in the opposite direction. It means it repels the external magnetic field. Well, for the current that's going to move in the wire here, okay, what circulation, think of it as a circulation, even though it's not circular, think of it as a circulation going from one end to the other or back around. What circulation will produce a magnetic field inside the loop that will repel this existing magnetic field? Well, the magnetic field inside the loop also has to be directed into the page. So in other words, that means that if I rotate my fingers around the loop this way, notice that my thumb goes into the page. So that means that the current in this loop would have to be this way in this part of the wire, go up in this part of the wire, and go back that way. So the positive is over here, the negative is over here. All right? This is pulling and moving positive charge this way through this. That's conventional current. Okay? And so that's how we're using Lenz's law to figure this out. Okay? And so that's the way that electricity is generated. Now, push it back in, it goes the opposite way. Pull it back out, and that's what I talked about with AC current. Now, if you remember when I showed you the electric motor, and the electric generator, okay? If you'll recall, here's the area that's exposed, and as you rotate this around, that's going to be changing the induced EMF in the coil. As that change happens, it's going to move current one way through it, flip it, and now it's going to start moving back the other way because the opposite field is facing it. Relative to the magnetic field across these field magnets here, that means that I get a switch in the flow. And that's why the commutator here or the slip rings here are necessary to deliver that changing current out into the world at large. All right? So as I would rotate this, it would generate an EMF in the coil, and then because this coil is connected either through the commutators or if I change it to the slip rings, that gets delivered out to the world at large by these other electrodes over here. Okay, and this is the way they do it at Niagara Falls. This is the way they do it at wind turbines. This is the way they do it at steam-powered power plants, whether it's a nuclear power plant or a coal-fired power plant or a gas-fired power plant. The energy of whatever is driving the armature of the generator, that gets converted into the electricity that then gets delivered out to the world. Now, there's a problem with that. Do we want direct current or do we want alternating current? Well, originally everybody was like, well, our batteries are all direct current, so why don't we use direct current? And that's what Thomas Edison did. All right, he built all of his generators so that they would be direct current machines. They all had commutators in them. Okay, and he would deliver direct current with his generators. And the reason they did this was because, well, if we have it connected through slip rings and we get this alternating current, this is the sort of output that you get. Okay? This is your AC output from a generator that's, you have its armature directly connected to the outside through slip rings. All right? Your EMF is going to start at a maximum when you have the maximum face, and it's going to decrease once it rotates 90 degrees, and then it's going to start going in the other direction as that face flips around, then it goes back up. And then you just keep rotating and go through, and this will go on forever. And the same thing happens with the current. When it's connected out, okay, so the current will also vary right with the voltage, okay? And we know that voltage times current gives us power. The problem with this is that this is not the same voltage throughout that whole cycle. And when you do the math of it, when you use the sine curves for both of these, when you do the math of it together, which I can do at a different time, I'm not going to do it here, taking the average of the voltage and the average of the current over time for AC power, it is equivalent to 1/2 of what you would get as if this were DC the whole time. That's the big thing that you got to remember. That the AC power delivered, on average, is half the power that you would get with the same device connected as a DC system. Okay? But what that meant was that your generators had to be built very close to what was being used because your current had to be very high. All right? If you're generating a voltage that was, say, 220 volts, which is what you want to use in your systems, you got to produce a lot of current for a lot of power. Okay? Well, that had drawbacks because if you try to push a lot of current through a long wire, we're talking kilometers long wire, that wire has a small but significant resistance for that distance. So you're losing a considerable amount of energy just pushing it through the wire to get it to where you want to use. Edison's vision was, okay, we'll create localized power generation systems, okay? And in a given small community, say suburbs weren't in existence yet. He was talking about cities, all right, specifically London and New York. And he was thinking that you would do community, local based power generators. And it would serve 100 homes, 50 homes, 20 homes, depending on the demand. Any factory would generate its own electricity right at where it was being used. So every factory building would have its own power generation room, if you will, on it. And that's a logical way of doing it. And in a lot of ways, we do that today. Think about all of the work sites that general contractors are doing their work that don't have electricity connected to them yet, and yet they're still using power tools. What are they using? Motorized electrical generators. Okay, fire them up, run them on gasoline, run them on diesel, and they're producing electricity locally. All right. Nikola Tesla was enamored of Niagara Falls. Wait, what? What's Niagara Falls have to do with electricity? Nikola Tesla was a very interesting figure in science. Look him up, read about him. He's weird, but he's also really, really, really cool. He was vacationing in Niagara Falls. The majesty of the falls, of course, was, something to behold. It still is something to behold. And so he wanted to figure out, how can I get all of that energy? Can I harness all of that energy? Wouldn't it be magnificent to harness all of that energy? He was friends with an industrialist by the name of George Westinghouse. And Westinghouse wanted to break into this new field of electrical generation, but he knew that Edison kind of had the clamps on it. And Westinghouse and Edison did not get along. Read about it. It's an amazing history. Tesla went back to Faraday's initial discoveries about electromagnetism and electromagnetic induction and said, what if we make this small change? Will that allow us to make electricity that we can then transmit vast distances with relatively small energy loss in the power lines, so that a remote power generating system can be used to generate electricity for someplace far away? Maybe, can the power of Niagara Falls be generated and transmitted across New York State to New York City to be used in the city, the greatest city in the world? Well, in his mind anyway. So here's how he took Faraday's idea and turned it into what we today known as electrical transformation or transformers. A transformer is not a robot in disguise, unfortunately. While I love, the whole idea, that's Hasbro did a great thing, and my son has great collections of it. The transformers we're talking about are the electrical kind. All right, it's an electrical device that transforms the induced EMF on one side of it across it and turns it into a different amount of EMF based upon a difference in the number of coils between the input side and the output side. Okay, so this is based upon Faraday's original concept of electromagnetic induction and how he demonstrated that would happen. So here we go. All right. Ignore the right-hand side over there. Start over here. Okay. Faraday's original experiment to demonstrate that you could get electricity through magnetism. He took an iron ring and he wrapped some wire around one side of it. And then he wrapped wire around the other side of it. He made sure that the wire was insulated from the iron ring. There was no electrical connection between this wire over here and that wire over here through the iron that it itself is a conductor, right? There's no electricity that's going to flow from this coil system over here to this coil system over here. Now, in 1830, in the 1820s and 1830s, they didn't have light bulbs yet. They hadn't been invented. Thomas Edison hadn't invented it yet, all right? But they did have meters, electromagnets on axles. They did have those. They were called galvanometers. And I demonstrated the use of that in a different video earlier, okay? So what he was able to show is when he closed the switch, that's what this symbol is, this is a switch. When he closed the switch, that caused a current to flow in this coil. So this current creates its own magnetic field here, and the iron aligns itself to that magnetic field. Well, as that alignment happens, that generates an EMF over here. The current goes from 0 to some value on this side of the coil. Well, that means that the magnetic field inside the iron ring goes from 0 to some value based upon the magnetism of this coil. Well, if it goes from 0 to some value, then that means that that changing magnetic field is cutting across these wires over here, creating a magnetic flux over here. And so while that change is happening, you get a reading on the meter. All right. He actually used the compass over here. Okay. He had wire wrapped around the compass and saw the compass needle deflect. He knew he had electricity being produced. Okay. So the consequence of this, though, was when you press the switch and you leave the current flowing, it only creates a momentary change over here. Once the magnetic field becomes steady, because the current in here is steady because this is a DC device, okay, then the magnetic field over here isn't changing. And since the magnetic field over here isn't changing, it's not inducing an EMF anymore. No changing magnetic field, no induced EMF. Switch this off, and now the magnetic field in the iron ring goes from some number to 0. Well, that change in magnetic field induces another EMF across this coil, and that causes a momentary flick over here. And so what he was able to show is every time he turned this on and every time he turned it off, he got the same flick going on over here on this side. Nikola Tesla says, what if I change the number of coils of wire. What if I use an AC generator, or even, that thing over there, and this generates a changing current in this coil? That changing current is going to generate a changing magnetic field in the iron ring. That changing magnetic field is going to induce a changing EMF here. Oh, but if I use a small number of wires here and a larger number of wires there, that means that I'm going to induce a greater EMF over here than what was applied over here. In other words, the voltage across this coil is going to be different than the voltage across this coil. And so as that happens, you get a change in the current. The current flow over here on this side is going to be a lot less because the bigger voltage doesn't need as much charge to move to carry the same energy. Certain amount of energy comes in here. That same energy is going to come out over here. Ideal transformer. Okay? It is this difference in the number of turns of wire between what we call the primary coil or the input coil and the secondary coil or the output coil that creates that difference in EMF between the primary and the secondary. It's what creates the difference in the voltage between the primary and the secondary. If the number of coils in the wire in the primary coil, the input side, is smaller than the number of coils in the secondary, then that means whatever input voltage I apply to it, could be 200 volts, becomes a bigger voltage in the secondary. The converse happens with the current because the power across the transformer must be the same. Okay? So a step-up transformer means that you are increasing the voltage across it. So we need to increase the voltage by increasing the number of turns from the primary coil to the secondary coil. All right, and that's what the picture was a moment ago. That was a step-up transformer. Now they're used at power plants. They take the, let's say 2,000 volts that is used to generate electricity, or is what's being generated, 2,000 volts and several thousand amps of current, because they're big generators. All right, and we're talking, a lot of power. All right, so 2,000 volts times, let's say 100 amps, and we've got 20,000 watts of power that's being produced by that generator. But if we try and push that 100 amps out through the, or 200,000 watts, excuse me, try and push that out through wires, it's going to cause the wires to heat up. It's going to cause the wires to melt. There's going to be a huge power loss, energy loss going through the wires. So Tesla proposed that, hey, we put that AC power on a transformer and we boost that 2,000 volts by 1,000 times, make it 2 million volts. Now we've reduced the current by 1,000. Because if you get a 1,000-fold increase in voltage, your current's got to go down by the same amount because your power across the transformer must be the same. Okay? So you go from 100 amps to 0.1 amps. Your energy loss across the transmission lines is considerably less because of that. Okay? And so that's why we use AC power, because now you can remotely generate electricity at one place, and you boost it up by a step-up transformer at the power generation station, and then where you need it, you put another transformer, and that steps it back down to the voltages that you need in your home, in your business, in your factory. That's why we use AC power rather than DC power to generate electricity on an industrial scale. Okay. Yep. This is a DC device. It uses a battery. Okay. And yet we have charging cords that have those little blocks on them. Those are transformers. They're doing two things. They are changing the AC from the power outlet, and they're stepping the voltage down, and then they're changing it into DC so that it can charge the battery in your phone. Alrighty. I'll see you on our next review session. This is your friendly heavy physics teacher signing off. Make sure you can check out the worksheets now. You should be able to complete all of them. I'll be sending out an answer for them. Have a great one, and stay healthy. See you soon. Have a good one.